so hello, welcome to the afternoon session of today. In the afternoon, we are going to have another sequence of 2 lectures on statistics and computation. At this time, mostly focused on the lower bounds. And again, we'll have, the speaker is an absolute expert in the field, Guy Bresler from MIT. Guy made major contributions in many areas, graphical models, other statistical problems. And as of recently, he's very interested in conditional lower bounds for statistical problems that he will tell us about today.
Great, thanks, Piotr. Hi, everyone. It's good to see all of you. So this is, as Piotr said, about average case complexity, in particular, average case complexity for statistics problems or data problems. So we have all these problems that we wish to understand. Are they computationally feasible or infeasible? Where are the fundamental limits of what's possible? This sounds very much like what computer science has been interested in from day one. What problems are feasible, what problems aren't. The distinction is that the inputs are typically sampled from some probability distribution. They're random. And that changes things completely. Now, on the other hand, statistics has been interested in exactly those sorts of problems, data problems. And the question there is, well, how much data do I need? Okay, well, that's been well studied for over 100 years, but at the same time, there hasn't been very much attention into understanding the computational limits for those questions. And so in the last 20 years, roughly, these two questions have kind of converged. And what I'm going to try to explain in today's 2 lectures is one way of reasoning about the computational complexity of statistics problems. All right, so I've been very interested and excited about this area for a while, and there's quite a bit to say at this point. Typically, I explain many different reductions and draw big webs connecting many different statistical problems. I'm going to do the exact opposite today. I'm going to focus on a single statistics problem and aim for all of you by the end of the 2 lectures to fully understand the complexity of this problem, both information theoretically or statistically, as well as computationally. Not only that, hopefully you'll understand exactly what this whole notion of average case reduction means for statistics problems, and maybe you can go and do your own average case reduction for your own favorite statistics problem. All right, so, okay, I see that if I point my head down, I'm suddenly 5 times louder, but apologies about that. So maybe one final just remark before I dive in. Because this is sort of at the interface of a couple of different fields or multiple different fields, there necessarily is various amounts of jargon and stuff. There's notation that I might use a different symbol than what you're comfortable with or whatever. So if anything is unfamiliar, just shout out at me, please, and interrupt, and I'll be happy to explain whatever convention or notation or whatever. All right, so the particular data problem that for us is our kind of prototypical example for today is something that's called biclustering. I see this really is quite loud. So I'm going to relocate this just a little bit. Hopefully that's not too soft. Is this fine? Okay. Okay, so this is biclustering. This is a problem that was studied by Ma and Wu. So that's Zhongming Ma and Yihong Wu in 2014. There are 3 parameters to this problem, n, k, and lambda. You'll see in a moment what those mean. So now the problem I'm going to phrase as a hypothesis testing problem. That's analogous for those of you who come from TCS and haven't seen hypothesis testing. That's just like the decision variant of a problem. And the setup is that we observe some matrix. It's an n by n matrix. And the goal is to decide between 2 different scenarios. The first is that xij, in other words, the entries of this matrix, are standard Gaussian, and they're sampled IID. Simple enough. This is just a pure noise matrix. Alternatively, there is some signal there. We first sample S and T uniformly amongst size K subsets. And then we sample Xij conditional on S and T as Gaussian with mean lambda and variance 1 if those entries are in S and T. So I is in S, J is in T, and otherwise the entries of this matrix are just IID standard Gaussian. Okay, so what does this look like? Well, there's a n by n matrix like this. There's a k by k submatrix. It's not necessarily contiguous. It's just easier to draw that way. Indexed by subsets S and T. Okay, each of size k. So maybe I'll just emphasize that. And in here, we have Gaussian with mean lambda, while out here, we have Gaussian with mean 0. All right, so now the setup is you observe this matrix. It's just a bunch of numbers. And your goal is to decide which of these two was the probability distributions that generated this matrix. Okay, so there are 3 parameters, n, k, and lambda. And looks simple enough. Oh.
We are guaranteed that one.
That's right. Yeah. So you're guaranteed that the x comes from one of these 2 distributions. So for those of you who are familiar with promise problems, this looks very much like a promise problem. But if you aren't, that's totally fine. Okay. So this is the problem. Now, one thing to emphasize is that.
So why this?
Sorry?
Why biclustering?
Oh, why is this problem relevant? Okay, so this is maybe interesting for some microarray analysis where there's some cluster of genes that are interacting in some way and lead to some data like this. It's been widely studied in statistics for several decades. Yeah, good question. Right, I should also emphasize that this is a sort of prototypical signal plus noise problem. We're trying to distinguish, is there a signal buried in noise or is it just pure noise? Is there a signal there at all? Right, so we're trying to decide between these 2. Now, of course, you could study the estimation or search version of this, where your goal is to find the planted signal. We could also say a lot of things about that, but we won't. We'll focus on this version. Most of what I will say will apply also to the estimation problem, with some caveats there. Okay, so given this, the goal is to decide which of these 2 is the truth, which of these 2 is generating our data. And just to be a little bit more specific about what that means, our task is to find an efficient algorithm, an efficient mapping phi that takes n by n matrix, outputs 0 or 1, corresponding to which hypothesis you believe to be true. And the total probability of error is going to be the probability under, does this show up? Oh, it does. So this is the probability under H0. So if H0 was the truth, that we make an error, in other words, that we output 1, plus the probability under H1. So if it was the case that H1 was true, but then we saw the data that was generated according to H1, and we output 0. So the goal is that the total probability of error, this is in statistics what's called type 1 plus type 2 error, we want that to go to 0 as n scales to infinity. All right. Okay, so one thing at this point to emphasize is that we have these parameters n, k, whoops, I switched to lambda, so I'm going to correct that. We have n, k, and lambda. And for every n, k, and lambda, this is a different problem. In particular, if k is bigger, then presumably the problem is easier. If lambda is bigger, the problem gets easier. Because in both of those situations, the signal is getting stronger. Right? And so we could ask the question now, for which tuples n, k, lambda is this problem feasible? And so in order to study this question, we're going to draw a sort of phase diagram. So we're going to plot here on the x-axis, alpha, k is going to scale like n to the alpha. And the y-axis, we'll plot the signal strength. Lambda is going to scale like n to the minus beta. Right, so as we go up, the signal gets weaker because beta gets stronger. As we move to the right, the planted signal, the planted submatrix is getting bigger. Okay, and so now for every point here, we can ask, is this feasible or not? And it turns out, as shown by Ma and Wu, that the following phase diagram explains pretty much everything that you'd ever want to know about this problem. So I'll just quickly draw it. Okay, so this point is half. This point is 1/3. And what they showed is, first off, that there are efficient algorithms that work when the parameters lie in this part of the region. There's also an efficient algorithm that works here. In this part of the region, the problem is downright impossible, information theoretically. So completely without regard to computational complexity, there just isn't enough signal there in order to distinguish the two hypotheses. And then in this final region, the problem is feasible in principle, but computationally hard. Okay, so this is more or less a complete answer to the question of for which tuples n, k, and lambda is this problem feasible or infeasible? And there's this somewhat more fine-grained answer, which is that there is this region where it's actually in principle feasible if you had unlimited computational power. However, it seems to be hard if you want to do it, let's say, in polynomial time. All right, so that's going to be the goal. We're going to try to actually explain every single sort of line that's showing up in this diagram. The first part, and it's only going to take maybe 10 or 15 minutes, is we're going to analyze actually simple algorithms that achieve the entire green region. Then we're going to analyze a simple algorithm that achieves the information theoretic limit, and then we'll move on to the meat of what we're trying to do, which is try to understand the hard region. Okay. So first things first, efficient algorithms. So I'm going to start with this region. I'm going to call it region 1. All right. So what is going on in region 1? Well, for one, beta is less than 0, right? We're below the horizontal axis there. So what is true? Well, lambda, which is equal to n to the minus beta, is then polynomially large in n, right? If beta is minus 0.01, and this is n to the 0.01. And so what this is telling us is that the entries are pretty big. So in terms of an efficient algorithm or a statistical test to distinguish between is there such a k by k planted matrix in there or not, it makes sense to perhaps look at the largest entry, the maximum. And so we're going to consider T max, which is an efficiently computable statistic of the n by n matrix, the data. It's just the maximum entry. Okay, so this is our statistic. Now, I claim that it works in region 1 in this green part of the region. How would we show that? Well, we can show that by analyzing the behavior of the statistic under H0 and under H1 and argue that based on the statistic, one can easily distinguish which setting we're in. And so let's start with H0. This is under H0. And so under H0, all of the Xij's are standard Gaussian. And so then just looking at the tail of the Gaussian distribution and doing a union bound immediately leads to that T max is less than, I don't know, square root of 4 log n with high probability. Okay. So is everybody comfortable with how one would show this lemma, right? We're just looking for a single Gaussian. It's the complementary CDF, right? The probability that Xij exceeds some value T. You just plug this in, you get e to the minus x squared up there, right? You plug it in and you get some polynomial thing, and then you take a union bound over the n squared entries. All right, cool. So that's the behavior under H0. What about under H1? Well, if Xij has mean lambda variance 1 for I in S, J, and T, then T max is greater or equal to, what should we put there? Well, we have k squared entries that have mean lambda. each of them has probability half of being bigger than lambda. So with high probability, the maximum entry is at least lambda. Sorry, what was that? We can actually just put lambda here if we want. Minus root 4 log n is fine too. Turns out it doesn't really matter. We could just put lambda, and the reason we can put lambda is because every single one of these entries in the planted submatrix, so this is the planted submatrix of size k by k, has probability half of being at least its mean, because the Gaussian distribution is symmetric. So now the probability that none of these exceeds its mean, lambda, is like 2 to the minus k squared or something. All right, so the maximum is at least lambda with high probability, and this is poly of n, and that exceeds square root of 4 log n. Okay, so that's it. So now you just threshold the statistic, and that allows one to distinguish between H0 and H1. Okay, so next we can move on to this region. This is region 2. Well, let's think, what's true about region 2? Well, we're further to the right in this diagram, so k is bigger, which means that this planted submatrix is bigger, which means there's a lot of entries that are a little bit bigger than they should be. However, we're up here, which means that lambda is kind of small, right? Beta is a little bit bigger there, lambda is kind of small. And so if you look at any particular entry, it's actually only a very tiny amount bigger than it should be. And so we need to do something that looks at more than one entry. And the natural thing to do is to compute the average. So I'll just emphasize here, there's many, maybe I'll just say slightly large entries. And the natural thing is to compute the average. And we're going to normalize by k. Whoops, we're not going to normalize by k. We're going to normalize by n. And add up here the entire matrix. All right. Okay, so now to check whether this works or not, we can do the same sort of exercise. So under H0, how does this statistic behave? Well, we're adding up n squared standard Gaussians, and then we're normalizing by n. So this is once again a standard Gaussian. Right, with variance 1, because when you divide by n, it actually divides the variance by n squared. Simple enough. What about H1? Well, in this case, it's once again a Gaussian. What is the mean of this Gaussian? Right, so just to remind you, maybe I'll draw the rest of the matrix here. We have this n by n matrix. We're adding up the whole thing. And these guys have mean lambda. Well, there's k squared things with mean lambda. And so the mean here is going to be k squared lambda over n, because we normalized by n. And still there's just variance 1, because the variance is added. There's independent entries there. All right, well, perfect. And what we see is that, sort of squish it here, apologies. So we see that if beta is less than 2 alpha minus 1, then this quantity will go to infinity. K squared lambda over n going to infinity is exactly the same as beta is less than 2 alpha minus 1 if you plug in k is n to the alpha and lambda is n to the minus beta. All right, and so our situation is that under H0, we have this one Gaussian that's just a standard Gaussian. And then under H1, the mean of this Gaussian is running off to infinity. And so choosing any slowly growing threshold will suffice to differentiate between the two hypotheses. Whoops, sorry about that. Thank you. That's a typo. Thank you.
So that the algorithm is actually different.
The algorithm is different in region 1 and region 2. Yeah,
We need to know.
that's right. That's right. Now, of course, you could just run the algorithm, like both algorithms, and then check. Yeah. Sorry?
0, 0 point.
The 0, 0 point. Good. So maybe I'll say something that's not exactly answering your question, but we'll see if it indirectly answers it. So because we're parameterizing everything here with the exponent of the polynomial, so like n to the alpha and n to the minus beta, everything here is up to sort of polynomial granularity. And so I actually won't say anything about exactly the point 0, 0. Now, 0, 0 is, I mean, kind of trivially information theoretically hard because k is a constant size, and if you could put any constant size thing in there, and lambda is also constant.
Yeah.
But
I would just
yeah, exactly. Yeah, no, it's a good sanity check, but I will also emphasize that everything I'm going to say is going to be, well, of course, this algorithmic analysis, you can do a sharp constant if you care about that. But everything else is going to be sort of up to some polylog, typically square root of log. So there's a little bit of loss there in terms of, these, basically you could think of it as these black lines here have a slight thickness. All right. Cool. Any questions about this? Yes, please. Sorry, you're saying why is the normalization 1 over n? Perfect question. Yeah, so the normalization is 1 over n so that the variance under H0 is 1. And the reason for that is when you normalize by n, you actually are normalizing the variance by n squared. Yeah. Good. Okay, so indeed, these are two extremely simple algorithms. Probably any of you would have come up with them in like 5 minutes if you'd sat with this problem for a bit and tried to solve it. And somewhat miraculously, these algorithms turn out to be optimal under some hardness assumption that we're going to go into. Before we do that, though, if people want, I can explain quickly what is the algorithm here. Maybe I will just do that independently of whether you want it. All right, so this is region 3 here. This diagram is getting a little bit complicated, but I'm going to explain what's happening at this line. Okay, and so in particular, this is the algorithm that achieves the information theoretic limit. It's tied up against this impossible region. So here we are, region 3. So what is the best algorithm that you can imagine? Well, we're going to sort of look around for this k by k submatrix. It's somewhere in there. We're going to look around for it. We're going to try to guess it. And if we guess it, then to kind of check that we did hopefully the right thing, we'll compute the average over that k by k submatrix. Right? And this in your head, if you think about non-deterministic polynomial time, and this is exactly sort of analogous to that. So you're going to do an exponential search, and then you're going to check for each instance, is this satisfying something that looks like a witness for H1? And so this is going to be, let's see, what did I call this thing? I don't know, I don't have a name for it, but I'll just call it T search. And this is the maximum over sets S and T of size K of 1 over K. And then the sum over the entries just in that submatrix. Right, and so again, maybe I'll just keep this matrix hanging around here. So here's our submatrix, and the entries are Gaussian with mean lambda. All right, so how well does this do? Well, again, we need to consider the distribution of the statistic under H0 and under H1. So let's start with H0. So under H0, we have the max of, well, if you fix, whoops, I see I wrote S twice, so it's S and T here. So if you fix S and T, then you have this a statistic that's just computing the average of some particular k by k submatrix. Right, and under H0, every k by k submatrix is just standard Gaussian entries. And so under H0, we're looking at roughly the maximum of how many such pairs of S and T there are. Well, it's n choose k squared. Any particular one of these is standard Gaussian. That's because we normalized by k here, and we're adding up k squared standard Gaussians. So if you fix S and T and we're in the H0 situation, then this entire quantity here is just a standard Gaussian for each fixed S and T. Right, and so we have n choose k quantities squared of them. And so you can, again, just do a union bound on the tail of the Gaussian to get that with high probability, T is bounded by a constant times square root of k log n. So what we see here is that as k grows, there are more possible locations of the planted submatrix. And so the value of the statistic is actually going up because we're taking the maximum of more and more different random variables. All right. So that's under H0. What about H1? Well, let's just consider the expectation of T. We know it to be at least k times lambda. Because if you choose exactly the correct S and T, then the mean is k times lambda. We're also taking the maximum of various other stuff, so it could go up, but it's at least k times lambda. And actually, T is greater than k times lambda. Let's say, just to be safe here, over square root log n with high probability. So we give ourselves a little buffer. All right, and so from this we can conclude that if lambda is big enough so that the statistic here is kind of running off to infinity more quickly under H1 than under H0. So that would mean that lambda is bigger than, let's say, log n over root k. Then I'll just say we can solve the problem. Okay, so what is lambda is bigger than log n over root k? Well, forget about the log n because, as I said, we're ignoring things that aren't polynomial factors. And so what is that? That's beta is less than alpha over 2. And well, we can go back here and we see that that's exactly this line 3, beta is less than alpha over 2. And so this algorithm succeeds in the entire hard region. Of course, as I emphasized before, it's not going to run in polynomial time because it's a search over all subsets of size k, actually pairs of subsets of size k, so even worse. And so this isn't efficiently computable. Okay, so at this point, if you're a statistician, this algorithm works for the whole hard region, yes. Exactly. All it depends on here in this analysis is beta is less than alpha over 2. So it actually continues to work all the way here. Maybe I'll make it red just to make it easier to see. I mean, you can extend this whole line. And it works all the way here, except for now we see that there's 2 different algorithms that work in the intersection of those 2 regions. The red. Sorry for those of you who are red-green colorblind. All right. Okay, so if you're a statistician at this point, you are feeling very uncomfortable because your goal in life is to find optimal algorithms, where optimal means that you achieve the information theoretic limit that's possible given the data that you have. And here, what one quickly realizes is that it's not clear if one can do that efficiently. And so all of a sudden we have to incorporate the notion of computational efficiency into our rates of estimation. We have to redo all of statistics from scratch. Okay, so this prompts us to sort of ask this question: how in the world are we going to reason about the hard region? Okay, so I'm going to emphasize a particular approach to reasoning about the hard region. That approach is reductions. So you've all seen reductions, for instance, reduction from 3 set to, I don't know, independent set, and so forth. So we're going to try to do exactly the same sort of thing. We're going to try to do reductions for these statistical problems, or for this particular statistical problem. And as we'll see, the main technical challenge is that we have to preserve the distribution. So it's not enough to consider the sort of reduction that works for worst case problems, for example, to show NP hardness, because the distribution at the output is something very weird. So maybe just to kind of quickly talk through an example. Suppose you start with a very natural distribution on 3 sat, let's say random formulas, uniformly at random, and then you do the textbook reduction to independent set. Well, how does that reduction go? Well, it takes each clause and produces a little 8-vertex gadget, a little subgraph, and then it stitches together these various subgraphs. If you think about it, even if you started with a uniform at random instance of 3 sat, the distribution on graphs is going to look very weird. It's going to have all these little gadgets placed in it and so forth. So it's not going to be a natural distribution on graphs. And so it's not going to achieve the sort of thing that we want, because here we have biclustering, and the statistician wants to assume that there's a very benign distribution over the input. It's Gaussian, and the planted thing looks like this. It's not some arbitrary, weird-looking distribution. So, so we want to do reductions, but we're going to need some different methodology. Okay, I guess I already wrote that. Okay, so with that said, I'm just going to briefly mention that here's a web of reductions, most of which were done jointly with my former student, Matt Brennan. If you get excited about reductions and you want to see all of these reductions, or at least some subset of them, you can look at my talk in the first workshop of the fall 2021 program. So from a year ago at Simon's. So you can look that up on the Simon's website, and I go through a bunch of the techniques and reductions that give rise to some parts of this web. I'll also mention that, my sincere apologies to anyone I forgot to cite, but yeah, I'm citing almost nobody, but some also quite interesting and formative works in sort of reductions for statistics problems that I'll just briefly mention are those of Berthet and Rigolet. Rigolet is here in the math department. Also, Renit has probably the first paper that I would consider a reduction from planted clique to a somewhat statistical problem in her 2008 paper with Noel Galvan and a bunch of other people, Alex Andoni, I don't know who else is there. And then also there's a really nice paper of Hayek, Wu, and Xu from Colt 2015 that does a really nice reduction to planet dense subgraph from planted clique. So anyway, that's just maybe a quick, advertisement for some of the literature. And then, like I said, I mean, there's been some progress creating this sort of web of reductions. There's a great deal left to do. So there's a lot more left to do than has been done. Okay, so at the root of this giant web, or small web, however you want to think of it, is this problem, planted clique. So for us, that's going to serve the purpose of K-sat or 3-sat, the source of hardness that we're going to assume is hard, and then we'll map to various statistical problems. And so I'll tell you next about planted clique after I answer maybe Piotr's question.
I have a dumb question. How many problems that can now put conditional lower bound? I mean, the average space.
I guess these in this diagram,
So about 2,000.
something like that. Yeah. So for these, I should say that the aim is to really nail the phase diagram. So a sort of complete phase diagram is what one aims for. And for most of these problems, we have a complete phase diagram. Yeah. Okay. All right. So what in the world is at the root? What's this planted clique problem? So just out of curiosity, can you raise your hand if you're familiar with planted clique? All right, awesome. So planted clique is going to be a new problem for a bunch of you, maybe most of you. And it's a delightful problem. It's sort of the simplest, cleanest, most elegant signal plus noise problem that you can imagine. Hopefully you like it as much as me. So the setup is that you observe a graph G on n vertices. The hypothesis testing variant has as H0 that G is a purely random graph. It comes from Gn half. Alternatively, G comes from the planted clique n comma k distribution, which is described by first sample a set S uniformly at random from all size k subsets of the vertices, and sample G from Gn half, and then place a clique on the set of vertices S. All right, so this just looks like an n vertex graph that's purely random. There's a k vertex subset that's a complete graph. Okay, now I'm drawing this sort of sparse graph, but it's not a sparse graph. The ambient edge density is half. All right, so we can draw a phase diagram for this problem as well. So here's alpha, and we're going to just parameterize k as n to the alpha. It's a one-dimensional phase diagram, so the only parameter is k here. The only free parameter is k. So here's 0, here's half. Half turns out to be important. See why? We'll state maybe a simple proposition, which is that if alpha is bigger than half, in other words, k is polynomially bigger than square root of n, then the following algorithm, it just outputs the indicator that the maximum degree is at least 3n log n succeeds. Whoops, I think that's actually wrong. So I'm going to erase it and write something that looks more correct. So instead, I'm going to write n over 2 plus let's do that. All right, so why is this a reasonable thing to do? Well, if we consider one of the clique vertices, then it's going to have basically a degree n over 2, but it's going to have sort of too high of a degree because it's neighboring all of the other clique vertices, and there's sort of bigger than root n of those people. The fluctuations in the degree of a non-clique vertex is of order root n. And so the neighboring clique vertices are going to boost the degree by more than the fluctuations. And so we get sort of a way to distinguish if there's a clique in there. Okay, so this is a very simple algorithm. It's kind of stupid, but it turns out to be up to polylog factors. Conjecturally optimal. I'm gonna just before I say anything about computation, I'll just give you an exercise. So the exercise is that the information theoretic limit is at k is 2 log n. Okay, so if k is bigger than 2 log n, there's an algorithm. It's not efficient. It's search overall size 2 plus epsilon log n subsets and check if there's a clique there. And if k is smaller than 2 log n, then it's impossible to tell if the clique of that size has been planted. So that's an exercise for you. You can use the second moment method to prove it. And for us, the more interesting threshold is at this half. And the conjecture is that there is no polynomial time algorithm in this entire region. Okay, so that remains a conjecture. It's a sort of conditional assumption for showing hardness. However, there's various evidence for it. So what does that even mean? Well, for instance, sum of squares algorithms of the sort that Sam described earlier today fail to solve planar clique in that region. And Sam was actually involved in that paper, as well as various others. Okay, so SOS algorithms fail to solve planar clique when alpha is less than half. Various other classes of algorithms also fail to solve planar clique. Various very smart people have worked hard to try to solve planar clique in that region and have all failed. And so it's a natural assumption to just, for now, put our hands up and say, all right, well, it seems like it's pretty hard in that region. It would be quite interesting if it wasn't hard. That would be cool too. So it's not like anyone is putting their life savings on it necessarily, but wouldn't be a terrible thing to do if you had to. All right. Maybe I'll just finish this diagram by putting the easy region here, which we achieved just by this max degree thing. Okay, cool. So that's planar clique. Let's see. So we're next going to try to talk about reductions. And so to talk about reductions, we need a definition. And luckily, this definition has been given a couple of times already. Sam most recently gave this definition. So you're by now experts about total variation. So this is a metric on probability distributions. We have two probability measures or distributions, mu and nu, on the same probability space. That jargon doesn't mean anything, then you can ignore it. We can define a distance between them. This is really just a half times the L1 distance of these viewed as functions if they have densities, for example. There are many equivalent characterizations that maybe aren't that obviously equivalent. So for one, it's the supremum over events or sets E of the difference in the measure assigned to E under mu and nu. And then there's also this coupling interpretation or coupling characterization that Sam gave, which is that the total variation between mu and nu is the infimum, or you think the minimum, of joint distributions over variables x and y, where x has marginal mu and y has marginal nu. So now we jointly couple them and we consider the probability that they're not equal. And if you minimize that probability, so you make them equal as much as possible, that is equal to the total variation. So maybe I'll just give an example here. I'll just ask, how many of you are comfortable with the total variation? Okay, so how many of you don't want me to describe the simplest scenario where one can easily compute the total variation, which is between two Bernoullis with different parameters? You've all sort of seen something like this? People have seen this? Who knows how to couple two Bernoullis? One with probability of heads 0.6 and one with probability of heads 0.4 in a way that's optimal, that achieves the TV.
Did you ask how many people don't want you to do it?
How many people know how to construct that coupling? All right, there's some hands, but not that many. So I'll just do it because it's, it's a cool thing and it'll just take 2 minutes. Okay, so here's the setup. We have Bernoulli P and we have Bernoulli Q. And let's let X be Bernoulli P, Y is Bernoulli Q. And so I'm going to construct for you a coupling of X and Y. So it's a joint description of how they behave. A priori, they're just two random variables. They're just two coins. They have nothing to do with one another. You could imagine just two independent coins. But the point is that that is a very bad coupling in the sense that, like, if X turns out to be 1, maybe we should somehow do something to Y to make it more likely to turn out to be 1, because we're trying to make them equal as often as possible. Okay, so what are we going to do? Well, we're just going to put P and Q on this interval here between 0 and 1, and we're going to sample U to be uniform on the interval 0 to 1. Let X equal the indicator that U is less than or equal to P, and Y is equal to the indicator that U is less than or equal to Q. And now you can check that the total variation distance, well, you can just compute it by writing out the PMF using this L1 definition here. We probably should have started with that, but we can just do that. It's going to be the sum over the possible values, that's just 0 and 1. In each case, the difference in probabilities is P minus Q. And we get that the TV of X and Y is equal to the absolute value of P minus Q. Okay, but now you can actually check that this coupling makes them equal with probability P minus Q. Right? Because if U lands anywhere down here, or up here, then they're going to both have the same value. They're going to both be 0 if it's in the bottom, and it's both be 1 if it's at the top. And so they're not equal with probability, sorry, I said equal, not equal with probability P minus Q, and that's the total variation distance. So we see that that's exactly, this coupling gives us exactly this. Any questions about this? Okay. All right, now one additional characterization of total variation, just because we're talking about hypothesis testing all this time, so I'd be remiss not to explain this. So in a hypothesis testing setup where you're given a sample X, either for mu or nu, the optimal probability of error in determining is it for mu or nu is actually given by this very clean and nice formula in terms of the total variation. So it's a half minus a half times the total variation between mu and nu. And you can check that this behaves as you would expect. Like if mu is equal to nu, then the TV is 0. And then given a sample, you just have no clue did it come from mu or nu because they're literally the same. And so your best possible guess is successful with probability half. And similarly, you can check that the TV goes to 1 if the supports of mu and nu are disjoint. So in that case, the probability of error will be 0 because you'll just be able to look and see the only way that this sample took this value was from mu or nu. Okay, so that's total variation. We can now define reductions in total variation. So if X is a sample from P, we're going to want to transform X to be a sample from some other distribution P prime described by the target problem. So for us, P prime is going to be this biclustering thing with the Gaussian. P is going to be planted clique. And so a reduction in total variation is an algorithm A that takes a sample X distributed according to P and maps it. So that's here. It maps it to something that has distribution that's close to P prime. Sorry, this isn't yet what a reduction is. This is just this notation of this arrow sub epsilon. Okay, so if a sample of X that has distribution P The algorithm takes the sample, produces something else. This L here is just notation for the distribution of the output of A applied to X. That's some new thing. If it's epsilon away from P prime, then we use this notation. P is mapped to P prime by algorithm A with error epsilon. That's this arrow sub epsilon. Everybody on board? All right, so now for reduction, what we have is well, what we want is an efficient algorithm A. So if we think about planted clique, we have actually two distributions, pH0, pH1. We think about biclustering, we again have two distributions, P prime H0, P prime H1. What we want is that the pure noise instance of planted clique gets mapped to the pure noise instance of biclustering, and similarly, the signal instance of planted clique gets mapped to the signal instance of biclustering. So one thing to emphasize is that A is one single algorithm, and it has no clue which of the two hypotheses is the truth. So it's oblivious to the input distribution. It just sees some matrix, some n by n matrix. And then it has to operate on this n by n matrix, and the hope is that if the matrix had distribution pH0, it maps to P prime H0, and similarly for H1. All right. Okay, so why is this useful? Why is this a good thing? Well, the reason it's useful is the following lemma. And so that's if phi delta solves, so I'll just use that as shorthand for the probability of type 1 plus type 2 probability of error is delta, solves problem P prime, then phi composed with A, delta plus epsilon solves problem P. Right, and so this is completely analogous to what you know and love from reductions for languages and, for instance, an NP or whatever. Right, it's just supposed to transform a no instance to a no instance and a yes instance to a yes instance, so that if you have an algorithm for the target problem and you would like to solve the source problem, then you can compose the two, right? So another way to think of it is someone gives you a problem P, you have no idea if it's a sample from H0 or H1. You apply the reduction, it produces then a corresponding sample for problem P prime. Your friend claims that they have an algorithm for problem P prime, so you're like, all right, cool, here's my problem instance, they solve it. And because you faithfully preserved H0, mapped H0 and H1 to H1, their answer is actually the same as the answer you're looking for the source problem. And so the logic here is the sort of logic you're all familiar with. All right. So maybe I'll just emphasize that this also means that if P is hard, then P prime is hard, right? By that same logic. Any questions? Yes, please.
Does or NA depend on the parameters? Problems like that.
Sorry, what was the question?
Like this algorithm A, does it depend on the parameters of the problem?
Ah, good question. Let me think. I mean, in general, yes. We tend to just assume that the parameters of the problem are known, and you can usually do some sort of search and map to many outputs. I think for this particular problem, it's not really necessary. Yeah, we'll see. We'll see. It's a good question. I think for this problem, it's not necessary. All right. And then maybe I'll just emphasize here, see also work of Levin from the 80s for a somewhat different notion of reduction for average case problems. This is a notion that's very close to a notion studied by Lecam in the 70s, statistician, but it also has this computational aspect. The reduction is supposed to be efficient, which Lecam didn't care about. But it's a notion that's very well suited to statistics problems. And the reason is just because this epsilon here, which is how close your output is to the thing you wish it was, that's what's showing up here. So the probability of error gets adjusted by the error in your output of the reduction. So that's why total variation is so convenient here. With that, I'll just, let's see, we'll revisit that in a moment. And I'll just state the sort of main theorem, which will be the goal of the second lecture, which is assuming that planet clique is hard for alpha is less than half, then biclustering has as its hard region the one that I claimed earlier on. And so I will fully be able to describe the reduction and all of its gory details. And most of the details in how one argues that the total variation from what is produced by the algorithm is close to what we hope it is. And so with that,